Now we're going to get a little more complex with these two-group disconnections. Let's look at an example. So we're going to think about cleaving a bond that puts these two groups in a 1-2 relationship. So we have the ether over here on this carbon, and then on this carbon we have the OH. So the carbon numbering is telling you the relationship of these two oxygen-containing groups. Let's add our retrosynthetic arrow and name the type of cleavage that we're going to do. We'll disconnect here, and this is a 1,2 dioxygen disconnection. Now let's draw our synthons. So just splitting this bond, here are the fragments we get. We talked about oxygen naturally having a negative polarity, so let's make this our donor synthon. And this carbon here will be our acceptor. I want to introduce a little more terminology now. This is actually a D1 synthon. The negative charge is right where the bond is going to form, so it's on that atom. And this is an acceptor synthon. It's an A2 synthon. Because this is 1-2 carbons away from where the functional group is, we can call this A2. Now we need to think about reagents, actual things we can buy. This pretty obviously can just have a proton on here, so this can come from benzyl alcohol. But how are we going to make this? In our last example, we saw putting on a leaving group, so maybe we could try that. So this synthon would be equivalent to a reagent like this. Now with this reagent, the reaction will be actually pretty tough. We have an alkoxide here, but this could get deprotonated too, and this is just kind of complicated. There's actually a better reagent that we can use. If we think about this oxygen as having lone pairs, and thinking about how it might interact with a positive charge next to it, well, we might think of using a lone pair and making a bond. Well, that would give us an epoxide. Hey, that's pretty great. Under basic conditions, epoxides add here at the least hindered carbon and open up quite smoothly to give a functional group similar to this. So let's show our forward synthesis. So if we treat benzyl alcohol with sodium hydride and then our epoxide, I've abbreviated the cyclohexyl C-hex, that'll give us our target molecule here. Let's call this synthesis A and do a new example, this time with oxygen and nitrogen in a 1-2 relationship. Now, the opening of an epoxide with an amine is not as reliable of a reaction. And so I'm going to show you a different way to disconnect this molecule to introduce a new reaction that gives the nitrogen and oxygen in the 1-2 relationship. I'm actually going to cleave this bond first and capitalize on the imine-forming reaction that we just learned, the reductive amination, so we can avoid any over-alkylation. This disconnection actually combines two steps if I show these as the starting materials for it. So I'm just going to add reduction here. Now I'm going to do another functional group interconversion of this to show you how this can actually come from a nitrile. Now cyanide is a nucleophile that can add into carbonyl compounds. So now maybe the disconnection for this will become a little bit more obvious. How would we get a carbonyl by disconnecting this? We'll need to cleave right here. So the anion of cyanide, so perhaps the reagent here could be sodium cyanide, will nucleophilically add here to this carbon. And this is the same type of disconnection that we can get with Grignard's, this 1,1 carbon-carbon disconnection. Let's look at a forward synthesis for this one. We'll treat our aldehyde with sodium cyanide, and we'll have to do a workup to protonate the alcohol. Now we can reduce this to get to our amine. Lithium aluminum hydride followed by a workup will do the job. And I've flipped the molecule over so it'll look like this. Now we can perform our reductive amination. So we'll treat with the aldehyde and then sodium borohydride to reduce the imine that forms. Here's the intermediate imine, and the sodium borohydride converts this to our target molecule. We try to be equal opportunity to all heteroatoms here, so now let's do an example with oxygen and sulfur in a 1-2 relationship. Now, if we start off with a functional group interconversion and imagine that this alcohol comes from a carbonyl compound, we'll open up a whole new type of reaction to give us this 1,2 relationship. Now, if we were to cleave on this side of sulfur, we'd have a whole lot of functional groups to introduce over here anyway on this piece, so it makes sense to do our disconnection to the right of sulfur here. Since sulfur is a nucleophilic atom, it makes sense to make this our donor synthon and put our negative charge on sulfur. This will put a positive charge on this carbon atom. Now we need to come up with some reagents that we'd use for this transformation. It makes sense that the sulfur-containing molecule comes from the thiol, or maybe the sodium salt of the thiol. And to make this carbon into an acceptor synthon, well, we can add a leaving group as we did before. These alpha halocarbonyl compounds are quite straightforward to make, so this is an excellent reagent for this reaction. We have this halide leaving group adjacent to the carbonyl, and these are great partners for the SN2 reaction. So we can imagine reacting these in an SN2 fashion to give this, and then doing a reduction to arrive at our final target molecule here. Let's look at some more two-group disconnections. All right, now we're going to look at an example where two oxygen atoms are in a 1,3 relationship. This compound is a beta-hydroxy ketone, and this is made by the aldol reaction. We have a carbonyl over here and an alcohol over here. The side in the aldol that retains the carbonyl was the side that enolized. So that means the carbon had a negative charge on it. So we'll draw our disconnection here. We'll name this a 1,3 dioxygen cleavage. And let's draw our synthons. Here we have a D2 synthon. The negative charge is on the second carbon from this oxygen. And this is an A1 synthon with the positive charge adjacent to the OH. Now with our epoxide, we thought about pushing electrons toward the positive charge. We're going to do the same thing here. And if we consider this, donating these electrons down, well, we'll see that this is actually equivalent to the ketone. So our synthon is equivalent to acetone, and this reaction can occur from the condensation of two molecules of acetone, one that is enolized and one that is not. Now, we need to remember that hydroxy ketones are not typically isolated from the aldol reaction. Often we treat these with acid or base, and they undergo dehydration quite readily. And a lot of the times, these reactions are under acidic or basic conditions, and so this is what you isolate. You actually don't get this. So the 1,3 relationship of two oxygens might not be as obvious here. But we just have to remember this one. When we see an enone, so this conjugated double bond with a carbonyl, we have to know that this is a great compound to form via the aldol reaction. In fact, this disconnection is so common, often this is not shown and will abbreviate by cleaving this bond in half, writing alpha beta over the arrow, and showing our starting materials. Let's look at an example when oxygen and nitrogen are in a 1,3 relationship. We have this compound. These R groups could be anything. We have two different R groups on here. And just like last time, we're going to use a nitrile to introduce this amine, but we're going to do it in a different way. So the first thing that we'll do here is a functional group interconversion to go to the nitrile. Now, nitriles, like carbonyl compounds, can enolize. This occurs adjacent to the cyano group and is very favorable due to resonance. So we can draw a disconnection right here. Bearing in mind that the nitrile enolizes readily, this will be our donor synthon. And let's draw what our acceptor is. Boy, and this looks a lot like what we had here, this A1 acceptor right here. So we can envision this coming from the aldehyde. So for our forward synthesis, which I'll just talk through in the interest of time, we'll take this nitrile without the negative charge, treat it with an appropriate base and form this. We can then add it to this aldehyde and work it up to get this molecule. Let's look at something with oxygen and sulfur in a 1,3 relationship to talk about one more really important reaction. As I mentioned at the beginning, it's often good to cleave next to a heteroatom. And if we cleaved over here, we'd have a lot of functional groups on this side of the molecule. So it makes sense to cleave right here on the right-hand side of sulfur so that we can join two pieces with different functionality. Sulfur is naturally a nucleophile, so this is an appropriate donor synthon. And our acceptor will look like this. Now, introducing a leaving group at this position isn't the easiest thing with a carbonyl compound. Remember, we like to add them right here, adjacent to the carbonyl, because that's an easy reaction, alpha halogenation. But here we would need a beta halogen. So actually, we can use a different compound to approach this. When an enone like this encounters a soft nucleophile, something with a negative charge that's really spread out and polarizable, well, the addition occurs at this carbon in a 1,4 or Michael addition fashion. So for our forward synthesis, we can treat this enone with perhaps the sodium salt of the parent thiol, followed by a workup to get our proton back. I almost feel like I don't know where to stop with this video. We could just look at so many more disconnections and different relationships of functional groups. There is one more that I want to point out. Ending with this feels kind of funny to just not mention it. So let me just show you one forward example to show you how we can get a 1,5 dioxygen relationship in a molecule with a reaction that's a Michael addition. So I'm not going to show this retrosynthetically, but I just want to point out this in the molecule, and then maybe I'll break the bond at the end. If we treat this with an enolate, so let's do the enolate of diethyl malonate, we'll get a conjugate addition. And I'm abbreviating this, we'll just add a proton somewhere in here. Let's show the product that we get from this overall process. So in one single step, we've created a 1, 2, 3, 4, 5 carbon relationship of these two functional groups. But when you see this relationship, it might not be so obvious because we have to remember that these esters undergo hydrolysis and decarboxylation quite readily. So if we treat this compound with acid and heat, we'll get this product. And our groups are still in the 1,5 relationship, but it's not quite so obvious that it came from this great enolate here that's really stabilized and easy to form. But this is a great way to form that 1,5 relationship. So for this example, our retrosynthetic disconnection would be right here. KP here. If you learned something, give me a thumbs up on the way out, and for more chemistry, subscribe to my channel.